Hello. Well, just a second. Hello, everyone. Today we welcome our own Roussanka Loukanova to tell us about dependent type theory of situated information with context assessments. She's part of our team, so don't need presentation. And without any further ado, you can start if you want.
Thank you very much, Vesco. So now I shall, just a moment, because okay. So just to give a very first overview of the history of this topic. For me, it's already a lifelong topic from my PhD thesis. So the topic has been introduced by John Barwise in 80s. By two works. The very first one, is the groundbreaking, and then he wrote a book together with John Perry. The book and the paper are, so to say, philosophical background or just ideas of the situation theory as an alternative theory for semantics, for computational semantics. At first, it was introduced, in the first paper, it was introduced by the idea of situation semantics. And immediately with the paper, it was realized, John Barwise realized that that's not going to work. The best way is to develop the theory as a theory of general information, and then the application to computational semantics of human language or any other language to be just a special case as an application. And as mathematicians, we know very well that that works much better in many cases when trying to solve a task. It's better to solve a general task, and the one that we are targeting just to be a special case or consequence. So then in 2018, Larry Moss and Jerry Seligman, they introduced already mathematics. So this is 2018, is a very, very detailed mathematics of situation theory as based on set theory, but non-well-founded set theory introduced by Peter Axel. So all of this works 1, 2, and 8. There is no language here. It's model theory, including the computational semantics, which is called situation semantics. These are pure model theories, although grounded on non-well-founded sets. In my dissertation, in between these works, I also took up the approach of model theory and applied it for semantics of natural language. So what I did there, I just did development of mathematics that were the ideas of which were in 1 and 2. And I introduced, so in 1 and 2, and also in 8, the idea was that propositions and types somehow didn't go together enough well mathematically. So there it occurred to me that types are not abstractions of informational pieces, but types are propositional objects, abstractions, lambda abstractions over propositions. So that was my major contribution there, and I stand for it up to now, but now I know how to do it better with Moskovakis recursion. So in 4 and 5, I already have started this idea because I already knew about Moskovakis paper in 2006. So here I already started from about 2005 actually I started, but I had a lot of other work, so I just worked intermittently. So I started in developing everything with a formal language, just like Moskovakis. So in 2006, Moskovakis introduced simply type theory of recursion with a formal language. And the recursion, the recursion structures, the mathematical structures of the functions are domains. So that's what I have started here by developing formal language, and the traditional model theory or situation theory is just the semantical counterpart of the formal language. So, but here in 14 and 19, I stayed with the idea, and I continue to be convinced of that, that simple types are not going to complete all the job for situational semantics and for situation theory, because we need situations to be much more detailed and much more grained than simply type theory can provide. So now I'm working between these two, developing the type theory with simple types, Muscovakis recursion, because there is a lot of mathematical machinery that needs to be developed. The latest one I am implementing, so to say, the mu operator, but without any coding. And also the type theory of Muscovakis, 2006, it is with Curry encoding of relations, multi-argument relations. And in this work that I present today, there is no Curry encoding, and there is a good reason about that. This is because we are targeting partiality, partial functions, and it also for application, it's better to work directly with objects without coding. Coding is quite heavy, so Schoenfinkel and Curry has been quite avoided by people working with applications of logic, namely because of that, because working with the coding is too heavy and one cannot see directly the task for the applications. So this is the history, including up to today what I do. So now, what shall I do here? I will keep everything as informal as I can, simply because also I'm developing a huge machinery that integrates several huge machineries, and there is no possibility to talk about everything together in details, technical, but I will give some formal definitions of the language pieces. The language itself, the formal definition, is a huge recursive definition by structural induction. It's very huge, and I just will give pieces of the points of the structural formation of the terms and give examples. So again, in this theory, I already use inside of the formal language of the dependent types, I use Muscovakis recursion inserted in relational form, and this also needs heavy work. At the end, I'll show what it needs. So here, all these dependent types are very close by nature to Per-Martin-Löf dependent types. So I ended up completely accidentally in Sweden, and on top of that, completely accidental. No, the second thing is not accidental. I am a logician, so I immediately became part of the group Uppsala Stockholm in logic, and it turns out that this is the group in which Per-Martin-Löf developed his dependent types. So Per-Martin-Löf dependent types is syntax. These are syntactical objects, much more detailed with respect to logical operators than anything else. Mine dependent types from my dissertation was also dependent types. I just didn't know to call them dependent types. So those types are recursively defined objects, and the recursion depends by mutual recursion on other objects, on other types and propositions. So similarly, like Per-Martin-Löf, the types in which I developed in situation theory are propositional objects. I'll show that in Per-Martin-Löf too. But mine was semantical model, mathematical model, while Per-Martin-Löf was syntax. And one of the biggest tasks from the introduction of Per Martin-Löf type theory was the semantics. So it is open problem up to now. So the precise relation between what I do and Per Martin-Löf dependent types is not yet known, but I immediately recognize that these are very similar by nature objects, and there are different dependent types nowadays. So the entire area is hugely open area, including Per Martin-Löf dependent types. This is hugely open area, but I'm very sure that there is a very close relation between the types, dependent types that I introduced, and Per Martin-Löf types. So it might be that actually I am working on providing semantics of Per Martin-Löf dependent types. I don't know, with some additional work and development, of course. So here in this, so I put this task aside because I cannot work on so many tasks. So I focused on development of Moskovakis the type theory, simply type theory, because there the calculi and the concepts of the propositions, they need development. That's my focus currently. It's pure mathematics, and I also try simultaneously to apply it to semantics of natural language and to some computational biology here and there. And in this paper, I initiated another task, integrating the dependent types of situated information with numerical data. This is very important, I think. And this is not going to be done easily. It can with coding, with Moskovakis simply type theory. Probably it can, I even don't try. I tried something with the verbs, with the morphology, inflection, and it becomes extraordinarily clumsy and untransparent. So it's very transparent with theory of situated information. So I'll show how it can be done even at two different levels. So now the idea here is in the red block. These ideas, they come from Barvai's ideas from his work on model theory of situated information, but I am transferring, I'm developing formal language for it. So information is presented going together with situations. Situations go into entire recursive structure of the situated propositions and the informational pieces, including locations, and the locations I am keeping them as a bundle, as one entity, space-time locations, but they can be separated. So one can have separately locations for space and separately locations for time. These ingredients are extraordinarily important for proper representation, proper modeling of information, biological approaches, while this can be used as in model theory by model operators. Here, the space-time locations are direct ingredients inside of the informational pieces, and therefore as ingredients of the situations. Also, the agents can be introduced very directly by informational pieces and situations. So here, situations, they are called, from the time of the introduction of situation theory, they were called small possible worlds, partial small possible worlds. So the difference is that here, these small partial possible worlds, they are not external. They are not the meta language. They are part of the informational pieces, and the informational pieces are part of the propositions. So in Moskovakis, 2006, this is already an idea introduced in his formal language with the simply type theories. I'll show where they appear. But as states is much less, much more quiet ingredients, while here the situations can be very rich with a lot of information in them. And here by Moskvakis, so the objects with partially available information. This is extraordinarily important. This is the original idea that the information must be, and the propositions and the informational pieces, they must be partial, not just partial functions, but with parametric objects, and the parametric objects can be components of the propositions and the informational pieces. So intuitively, parameters are semantical objects, but here in the formal language, they correspond to variables. And the idea of Moskvakis dividing the variables in two kinds, proper and recursion or memory variables, extraordinarily important. And on the top of that, I am developing the notion of a complex restricted parameter, semantic parameter, or complex restricted variable. And this is the new that I'm introducing now with the formal language. I introduced it in my dissertation. That's one of my contributions there, but I introduced it again recursively like here, but in model theory, in model objects, in restricted parameters as semantical objects. And it is very difficult to work with the model theory, with objects of model theory, while with the formal language, everything goes much smoother and much nicer with the recursive definitions, etc., including restrictions. So the restrictor operator is doing the magic here with the magical tool, and it corresponds to the mu operator. So the last thing, objects in nature. I have this, I have done only a little bit by trying to model receptors for neuroscience. And that I believe must be done again, like here, by integration with numerical data for strength of the connections between the neurons. But the lambda abstraction and the recursive restrictions and the recursive assignments are significant part of this modeling biological entities. Probably just cells, and even probably DNA. DNA has been very successfully modeled by automata theory, but also coupled with statistical approaches because of the large amount of neurons there in the cells, the DNA cells. So here I start immediately with the very basic formal basics, but this is just the primitive objects, the primitive types of the this new dependent type theory. So here with the blue, I have underlined, I pointed which basic types are available in Moskvakis type theory of recursion. So individual int, this is a constant, and this is a primitive type corresponding to the type E for entities in Moskvakis recursion and also in Gallin intentional logic. So another one is the polarity. The polarity, I have underlined it with magenta, not with blue, because actually it reminds, only recalls for truth values, but these are not truth values. The truth values are of type T in Moskvakis. Here, they remind only, but they are not truth values. So eval, this is the new entity, that type that I'm introducing today. This is actually what corresponds to the truth types, but I have not only 0, 1, I'm entering possibilities for values, the entire spectrum of real numbers. So here relation in Muscovaci's type theory, this is recursively defined types. It corresponds to entire spectrum of recursively defined functional types. Here, I also have recursively defined types for relations. I'll show them. But here there is one which is basic type. It's just the type of any term which designates a relation between objects. So the new thing here is argument rows. I better don't talk right now about them, but I'll come back to this. They correspond intuitively right now. They correspond to the indexing of the arguments of the functions and the relations in mathematics. This is, none of us is thinking about calling, naming the arguments of the functions with some other indexing function than the indexing function from numbers from 1 to n. So ith argument slot of the function is actually argument row. But here it's, I'll show, it's much more like here we go to the basics without necessarily indexing the argument rows of the relations and the functions and also of the types with a numerical ordering. Although it can be done and often we do it. Location log, this is the basic type for the locations. And now I shall stop talking about this, but these are the basic. On the way I show, so this term style, the double term style, is familiar to all of us as the relation between models on the left-hand side and on the right-hand side for formulae, for terms, propositions. This is already type, basic type, and it is part of the language itself. And it is also part of the terms for propositions. So I show later that. So intuitively here, for these models, basic types, so the propositions, so this is what we see in models in semantics of classical logic. So S is some model, mathematical structure, and sigma is some formula. Here, S is a situation and sigma is the informational piece, and this is an expression, formal expression of the language itself, the formal language. So actually, this models is a type, and this type has two argument slots. One is for situations, and another one is for informs. Without the parentheses, here I designate a proposition that has been verified, and this is actually has been open question to myself. But now, with by introducing these assessments, I think I already know how to model it with this value when evaluation is corresponding to verification. Then, for example, in the database, we may have verified propositions. So the types are the most complex, the complex ones. These are the basic ones. And then in the typical way, by recursion, we can define complex types, and the complex types are defined at stages. So here, to avoid the complexity of non-well-founded sets, here I follow the idea from Martin-Löf. One doesn't need to think about all of the types, the class of the types, because it's a class, it should be class. We shouldn't need to have them generated, all of them, the entire class. They are generated at stages S to some level K or N as needed on the especially for applications, that's very important. Abstractly, theoretically, one can work with non-well-founded sets and say this is a proper class, which is a non-well-founded set. So here, like before, we have constants. All of them are typed, pure variables, and recursion variables. In my dissertation, I put this, I blended them without being, without occurring to me to separate. So Moskvakis introduced this separation very well. And then here I shall use notation, typical notations, because the terms are very complex, and sometimes one needs to point the type of the components. So I use the notation that is more flexible to see the type assignments, either with a with a colon or with superscripts, sometimes even with subscripts, or just telling that the term A is part of the terms of type tau. So now here comes the argument rows. Each relation, function, and each type, they come with a set of argument rows. In mathematics, functions and relations, they come with argument rows, with argument slots. Just they are indexed by numbers. If gamma is a function of n arguments, then the argument rows, argument slots of this function are encoded by the numbers 1 to n, and we order them and we put them in parentheses. Here is very important, especially for languages and for other applications. It's better that we continue to use indexing function, but without assuming that the indexing function is by numbers and that they are ordered. So again, here in classic argument rows of gamma, usually this is 1, 2, 3, 5 or 1,000 argument rows and argument slots. And then we use the application. So here I'll show how I avoid application, but although application can be also defined, especially for functions. I don't think I have included anything about that in the presentation, but in a classical way, lambda abstracts terms, I show how they are formed. They can be used in forming application terms. And then it's very important that here the application is not according to the numerical order, but according to filling up these argument rows with the values, with the arguments themselves. So argument rows, they get filled up with argument values, assignments, and not necessarily ordered, but we can order. We are very skillful as mathematicians to do that, to order them. But then one puzzles, one who works, even if you encoded them by order, when you work with many objects and with applications, then you are puzzled which object fills what argument rows. So in one of the previous seminars, I think it was in 2019, Veselin Drensky, he asked me, how do you model, how do you represent a sentence like Ivan Vazov, Chete Ivan Vazov? In Bulgarian, there is no, or in English, the first name, the first occurrence of the name designates the individual that is the reader. And the second one, the complement, is the object that is read. Papers written, books written by the author Ivan Vazov. So in English, they are ordered and we can designate them by order, but the Bulgarian sentence is very ambiguous and we better use argument rows. I show exactly such an example, argument rows without any indexing to avoid ambiguity. So now the infos are these objects. So 7a is an informational unit. Barweis called them informs. So these informational units, they look like tuples, and they are tuples. So this comma here is leftover something, so you forget about it. So the first component is the relation term. So gamma is a relational term. And then the next components are filling up the argument rows of gamma with objects. So arg1 is an argument row, and it is filled up by some expression designating some object. So now it's crucial, it's very important that these argument rows, they come with type restrictions. So Muscovaci's recursion is giving very good possibility for all of these objects to be defined, not in a clumsy way, piled up one over the other, but by recursive assignments. While I introduced such that to say that the argument row A1, argument 1, must be of type T1. The object filling this argument must be object or term of type T1. So this is the notational tool. In the formal language, actually, I abandoned here in the presentation. Actually, here I use each one component here as a three elements. On the left side of argument 1, I put the restriction, what kind of object is allowed to fill up this argument slot. And on the right hand side, instead of maps to, is again a column for the object filling up that argument row. So in mathematics, this left part of each element here is skipped. Everything is ordered, is indexed by first argument row, second and argument row. So we don't need these notations there because we work with encoding. That can be done here too. 7b is exactly that. Gamma is a relation, and its arguments are Xi1 to Xn. So this saves space and time. So mathematicians are skillful in doing this, namely for that reason, to avoid these clumsy expressions. But these clumsy expressions are necessarily for many purposes, and for especially in data and in semantics, especially for computational semantics of natural language. These arguments are better not encoded by numbers, because then it's not clear which argument row Xi fills up in such encoding. And when there are a lot, then that information gets lost. So now, here is an example. Again, with 7a or 7b, these are the classical propositional formulas. Each such expression is a term for a proposition. So here we forget about it. This is not a proposition. This is just informational entity telling that whether this information is factual or fictitious, that's a separate issue. But this is an informational unit carrying the information that supposedly these objects Xi1 to Xn terms are filling up the argument rows of the relation gamma, carrying the information that the object designated by these terms are supposedly in the relation gamma. So here I go to the example with the reading. So read 2 is a constant. Here we assume that it's a constant. It depends on the application system. So here we assume that this is a basic constant for a relation, and this relation has several argument rows. It can have just 2 argument rows. Natural language sentences are very forgiving, especially Bulgarian language. It can skip quite many of the arguments of the relations, but in English it requires at least 2. John reads Mary's books. But here John reads Mary's books to his child. We may have another yet argument row. So here we have 3, I assume at least 3 argument rows, 1 for the reader, 1 for the object that is read it, and 1 for a listener. The listener might be just the reader himself. So CC can be the same object as CA. Also, the informational units typically come with 2 additional argument rows, 2 additional argument slots, 1 for the space-time location. So this relation applies to these objects in those rows. In location L can be compound space-time location. And in the original Barwise situation theory, polarity was 0 or 1. Here I am changing it. I actually changed this in a couple of years in a paper about this with, so to say, degree or the level to which this informational unit is carried on. So the relation of reading to is, so to say, fulfilled to this degree. If I assume that the values here are numbers between 0 and 1, so here read to is 60%. So maybe the reader reads 60% of his time or something like that, or in the database, this informational unit is coming with this polarity. So the database has to be checked, and this number has to be filled up according to the applicational system, data system. So have in mind that here I assume that CA, CB, and CC are either constants or recursion variables. I prefer them recursion variables, and these recursion variables can be instantiated. Similarly for L, very often we don't know the exact time location, only I'll show how to impose that. We only know restrictions about the time in the past or in the future or in time coinciding with the time of the some utterance. So here just this info carries that there is a location in which this relation is fulfilled. So now there is no way in our world, maybe in some other worlds that we don't know anything about, that the relations like this, that are not mathematical abstract relations between numbers, etc., all other relations in the world, they happen in space and in time. So why not? So that idea was introduced by John Barwise, polarity 2. And again, this is not truth value because there is no proposition here. So here we can replace some of these parametrics, some of these recursion variables with pure variables. And the reason is very serious. With pure variables, we can do lambda abstractions. So we can abstract over Z, but we cannot abstract away from CA, CB, and P if they are recursion variables. Recursion variables, they correspond to the memory slots, and those memory, they can be filled up. The values can be assigned to them by the assignment operator introduced by Muskwakis. That's a magical thing. So I still don't come to it. So here is a very complex, I can come back to this too. a little bit later. For functions, to come back to the functions, just they can be considered as relations, and if gamma is a term for a function, all of its argument rows can be here, and one of the argument rows is for a value. But there is so this argument row can be value argument can be part of this set. But I prefer to separate them, and there is a very serious reason for that. Any application term, when we have a function gamma applied to its arguments here, argument 1, argument n, filled up with some objects, that this term represents directly evaluation, the value. This application term is the value. Here we better abandon this, and the value is separately coupled with the application term. So I will not come back to this those terms, because I even haven't completed that work yet, but that's the idea. So here the info terms, I gave an example, but here is the general pattern. The general pattern is this: any tuple where one of the first one is for a relation, and then there is a set of argument rows with their assignments, is an info. And T is of the type of the numbers, not necessarily numbers between 0 and 1, not necessarily 0 or 1. So the additional idea was that the polarity, either the relation holds or the relation doesn't hold, without being true value. Here I switch it to a degree. Relation fills up to some certain degree. So again, here each one of these has requirements. These are the set of the argument rows, and the terms that fill up the argument rows, they must be of the corresponding types. And tau is a location, space-time location. This can be separated again, and T is a numerical value. So now, here, before I go to those heavy propositional abstractions, here is an example for complex infos. And here, to save some space, I'm mixing up linear notation. So actually, this argument row assignments, this is, again, to come back here, actually all of this order tuple, this is a linear notation. This is just a function, indexing function. And the indexing function assigns values to the indexed rows, slots. So here, I is a conjunction of two infos. While here I'm using the symbol conjunction, it can be a comma. A comma corresponds to both of them. But comma cannot be used for disjunction because the informational units can be also disjunctional, so I don't touch them right now. And this is very important because Barwise developed so-called hating algebra of infos. So if one includes here logical connectors between informational units and the negation, then one gets hating algebra, just without thinking about the situations, only about the infos. And Eric Fenstad, he developed very well this info algebra in a special book together with other co-authors, developed the hating algebra for inserting it into a single situation. And it's still partial hating algebra. The negations, so there is a negation of infos, it doesn't correspond to negating the polarity 0, 1. So this work has one, if one wants, I don't have time, I have more tasks, but one can concentrate again on the info algebra by generalizing these polarities with numbers between 0, 1 or any real numbers. So one can abstract over informs, even when they're complex, and it's very useful. And the result is not a proposition, the result is a relation. For example, if here, the reader here is a pure variable, and Z, filling up the role of the listener, is a pure variable, we can abstract over them, and the result is a relation. So in the book, Barvai's book, these were called informally, intuitively types. I abandoned that. The types are much more complex objects over propositions. This is a relation. This is the relation between reader and listener. In specific, reading specific object B in a specific location L with polarity 1. And so the book is with that, and here L, the property of being a book, B, the location coincides with the location of the reading, but this location L here can be much more, the book existed before the reading and after reading, so it can be a different one. I have examples with them. So again, there is no proposition here. There are informational units and recursive definition of complex relations. This can be also functions if the inform corresponds to a relation which is a function, and one of the argument rows can be the value. So now I go back to that complex example, but before the complex example, I go again to one more heavy definition. The definition of the types. So the definition of the types, complex, we had the basic types, but the definition of the complex types, they require definition by mutual recursion, the definition of a proposition. So here is the interplay between complex or basic types and the propositions, basic or complex. So a proposition is an object, 21a, is a proposition of this proposition expression that has this structure. So assuming that gamma is a type, is a term for type, and this term has argument rows. All types, they also come like relations, also come with argument rows. And the argument rows also come with restrictions requiring corresponding types. So because of this argument rows, that was initially the mixture in the ideas of situation theory. That's why the objects here that I showed here, they were mixed up with types, because here we still have argument rows created recursively. But these are, so types, complex types, they can be also lambda abstracts. I'll show the formal definition, but they are propositional objects. So if gamma is a type, simple or propositional type, then this type can be filled up with specific objects of the corresponding types, and then we get a proposition. So this 21a is from my dissertation. So I assumed that, just like in logic, that when we write a proposition, they assume the default truth value. The proposition claims or states that this proposition is true, that can be true or false when the model comes. Here in this paper, I am extending this idea. So the types, they come with one more argument row for evaluations, and the value, the object that fills up this argument slot, can be a real number or can be any number any value that is kind of a certainty or degree of truth, something like that, reliability or something. So I assume by myself that the value here is true to a certain degree, and that can be any real number. So actually here, one of the possible argument rows can be certainty or reliability. So certainty, it seems quite a good argument row. So certainty is again a constant for argument row that is of the type eval. So in a specific proposition, this argument slot is of type for evaluation. So eval is a basic type introduced at the beginning, and T is filling up this argument row. So this is the new item. And in this way, we have two layers of assessments in a database, for example. One is for the informational units, to what degree an informational unit is factual or hypothetical, and the proposition is about stating to what degree this these objects are of type gamma. So Xi1 to Xn to Xn, all of them, the proposition intuitively says these are objects of type gamma. So the propositions here are not directly stating that objects are of certain relation gamma. That is in the info. The propositions, they state that certain objects, Xi1 to Xn, are of type gamma. And by mutual recursion, the informational pieces, the relations, they go inside. So I'll come back to more, but I go back to the examples. Here is inside of the red, I have a simple, no. Here I have a very complex proposition, conjunctive proposition. So everything between the red brackets is a disjunctive proposition. The first one between 11a, between A and D is one proposition, and it's in disjunction with another proposition between E and H. So intuitively, the first proposition tells that X, the object designated, evaluated by, so X is a variable, pure variable. It can be valued by variable assignment only to objects that are individuals, entities in the domain, semantical domain. So they are of type int. And here it states this informational unit, this inside the angles, this is informational piece, and this informational piece tells that X is a human in certain location D, and here the polarity is 1, so it's kind of affirmative informational unit. But then the proposition states that this informational unit is supported, it is available in the situation S1, 50%. So this situation S1 supports this informational unit 50% somehow. So maybe in the database we have 50% informational pieces, 50% of the informational pieces that claim something is exactly this info, claiming about this info. But also 50%, there is another proposition, evaluated also 50%, that is a humanoid. It doesn't need to be human. This might be a robot. So this complex proposition, this junctional proposition, then we have abstraction over this object, and we create a type. So this is the type of the objects X, which are either human or a robot humanoid, 50-50% in the situation S1. I think it's a very intuitive description after one tells you, if I manage to say, and this is a type. So the type is a propositional type. If I have had this lambda abstracts inside, in front of the angles, I will have type, I will have relations. So here is another yet similar entity, two types actually, that I will need, that we usually need, but it is not included. We need for a relation like read2. There is one detail here. So read2, as in the previous example, I associate it with 3 argument rows by skipping as default the argument role for space-time, but formally it has to be included here. But to make the expressions simple, I assume they are there by default for location, space-time location, and for polarity. So here, in general, I cannot say usually in class by using typical logic expressions, one can put a long conjunction saying that A reads B to C, and A is a reader, B is human, and B, etc., etc. So that is a propositional long statement. And usually when we say John reads Mary's books, we don't say John is the reader, Mary's books is the object read it. Those are hidden. They are at the semantical level, not at the syntactical level of the expression, but they are there. We comprehend them as human beings in a magical way. In formal system, all this has to be expressed, and it better not be expressed as a long, big conjunction. So what are the objects that John is the reader, filling up the argument role of the reader? It comes with restrictions that John is either a human or a device. So TA1 is a restriction, not a conjunction together with a major statement. John reads B to C. It's not a conjunction, it's a simple predication. Read to 3 argument rows plus 1 for time space and 1 for polarity. But there are restrictions. So the reader has to be either human or device. Before the era of devices, it will be just only the human reading. And written T0 is the object that has to be written somehow. And the listener is also either a human or a device, TA1. So there even more, this can be done even more realistically. So these two, TA1 for reader and for listener, and TA1, this, the listener can come with another type like TA1, but with different space-time locations, because the listener may listen only part of the reading time, or he can continue, the object, the listener can continue trying to listen, but there is no reading. So that's why in the reality, this can be even more complex. So to go now back to abstraction. Abstraction is also part of the formation rules. So I show that when examples and formal definition, that when we abstract, when we have lambda abstraction of informs, then we get relation. When we have lambda abstractions of propositions, then we get types, expressions of lambda abstracts over propositions are types. But we can have also lambda abstracts on terms phi that are not infos and that are not types. Those are, this is the typical even in any lambda calculi. The result is a function from Xi1 to Xn to object to term phi. So the same here. The only thing is that I distinctively separate one additional argument role for the value that is done in by currying in Muscovakis recursion by the error notation. There is but everything there is just lambda abstraction over one variable Xi1. Here it can be over set of variables. There is another thing. This is lambda abstraction over sets of pure variables. They don't need to be ordered tuples. Typically in relational lambda abstraction, this is a tuple, ordered tuple. And ordered tuple, this can be done here too, assumes that the argument rows are ordered. Here the argument rows are indexed by function from any argument rows to slots, so filter by object, so there is no need for ordering them, but there is a possibility for encoding them. So here are the argument rows. So lambda abstracts, they create their own argument rows in the three cases similarly. So each lambda abstraction over each one of these variables. One important detail, these variables can be pure, they cannot be recursion variables. Here there is a division of the job between these two kinds of variables in all types. So when we abstract over a term phi, the abstraction, lambda abstraction, creates corresponding argument rows. And here it's again part of the entire huge recursive machinery. So the type of each one of these argument rows, the type of Xi1 is, do I have time?
No, I believe the Vasilin is too modest to do his job and remind you it's time is up. So please summarize the rest.
Yes, I am
in a couple of sentences, if possible.
Yeah. Yes, just to say, because these three examples, they are the same, just the details are different, but the argument, the type restriction is actually a collection. Xi1 fills up different, has different, can have many occurrences in phi, and each occurrence has its argument restriction. So T1 collects as a set of all those type restrictions. It's not just one type, it's a T1 to Tn. These are all collected corresponding restrictions. So it's a huge recursive machinery of the complex. So this is it. I think I have finished. Thank you for giving me extra time. I see that I am 4 minutes over.
Are there any questions? If not, let's thank the speaker. You don't do that?
Thank you for listening to me. Sure. It seems that I have been talking to myself. The truth is that this is a huge machinery. It is a huge, huge machinery. Part of it, small part of it is classical logic, but logic is there. And that has to be developed.
Okay, excellent.
This has been used for years in one of the largest computational large-scale grammars of human language. In a naive way, but it has been used.